Welcome to this Forge College Explainer. I'm so glad you're here for bytecode execution patterns and next steps. Now, I know we literally just took a quick, exciting hop across the cryptoverse in our last lesson, configuring Claude Code for Solana skills, but today we're jumping right back into Ethereum EVM. Grab your hard hats because we are getting technical as we continue our Ethereum fundamentals journey, specifically inside the EVM Deep Dive Execution and Environment module.
It's kind of funny, right? It's a dizzying jump going from the breezy world of Solana back into the complex, heavy machinery of Ethereum. But hey, I promise you're in good hands. Today, we're going to look at the EVM blueprint strictly from the perspective of an architect. We aren't just staring at lines of code today. We're taking a step back to look at the structural patterns that actually make this engine hum.
Here's our blueprint for today. We're going to go from opcodes to patterns, look at initialization versus runtime flows, map out calls, returns, and reverts, map the overall execution blueprint, validate our flowchart, and then wrap up with some next steps. Let's get into it.
From opcodes to patterns, and spotting those repeating motifs.
So if you've ever looked at a raw execution trace, you know it's basically like reading the code from the matrix. It's totally overwhelming. But instead of treating every single opcode like some novel, isolated event, you gotta look for the foundational instruction lifecycle. Every single instruction does this. It fetches and decodes the opcode, updates the stack, charges gas, performs side effects, and finally reaches termination. Once you internalize this deterministic cycle, the entire trace stops looking like a random wall of text and starts looking like a highly predictable machine.
Moving right along to Section 2, initialization versus runtime flow. These are two totally distinct phases. We can actually separate a smart contract's lifecycle into two distinct phases. First up is the initialization flow. Think of this as the one-time mechanical setup. You'll spot this in a trace because there's a heavy sequence of push operations. It's literally pushing initial data onto the stack and into memory and setting up the initial storage. It's basically the constructor running, laying down the tracks before the train departs.
Now contrast that setup with the runtime flow. Once that initialization is done, the runtime flow is the main looping mechanism. It's the daily grind of the contract's machinery. This is the path that executes every single time someone interacts with a deployed contract. And here's a pro tip. Visually separating this one-time setup from the repeated runtime path is going to save you hours when you're diagnosing a complex trace.
Section 3. Calls, returns, and reverts. This is all about mapping external communication.
Let's look at how the contract talks to the outside world and how it handles failures. The crucial point here is mapping the call and return handshake. Whether your trace hits an external call, a call code, or a delegate call, to borrow another contract's logic, you absolutely need to track exactly where stack arguments and gas are handed off. You're mapping how one process seamlessly delegates its resources to the next.
But what happens when the engine hits a wall? Here, we're contrasting a successful, graceful return termination with the dreaded revert or out-of-gas exception path. Notice how these control flow error idioms drastically alter the termination path. When you're making your diagrams, you absolutely must distinguish a normal return from a revert because they represent two entirely different states of the EVM machinery.
All right, Section 4, the execution blueprint. It's time to draw your own diagram. So let's roll up our sleeves and actually draw our own pattern diagram for the EVM. We're going to do a quick 3-step mini project to convert a massive, terrifying JSON trace into a clean, minimalist visual flowchart. Step 1, we parse the raw JSON trace. Step 2, we extract the control flow nodes and stack touchpoints. And step 3, we emit a mermaid or dot diagram that we can actually read.
Take a look at this. This is the raw material our Python starter script, let's just call it trace_to_mermaid.py, will digest to create those node identifiers. We look at the program counter, or PC, the opcode itself, and a snapshot of the stack before and after the operation. If you feed this structured JSON into our script, it does the heavy lifting of mapping the execution for you.
The script then outputs a mermaid flow description. By extracting those nodes, we can visually map the sequential flow edges, and more importantly, the conditional jump targets. Those are the specific spots where the code decides to branch. So instead of scrolling through hundreds of lines of text trying to remember where a jump landed, you just look at the branching arrows. It's super cool. It turns a massive text file into a really clear visual map.
Section 5. Validating your flowchart by checking the criteria.
Look, a blueprint isn't worth much if the engine explodes when you build it, right? So validate your work against this checklist. First, is your contract's entry PC verified?
Second, did you successfully locate and label the external call branch? Third, is your revert path clearly distinguished? And finally, does your diagram mark memory writes with an M for mstore and long-term storage loads with an S for sload?
The core philosophy behind this whole exercise is pretty simple. Clarity trumps exhaustiveness. I really want you to remember that the goal here is to create a useful navigational tool that you can explain to a peer in under 3 minutes. We aren't trying to create a perfect, exhaustive replica of every single instruction. We're just collapsing familiar sequences into single nodes so you can focus your energy on the unfamiliar parts.
And finally, Section 6, Next Steps and Memory Allocation Prep.
All right, here is your homework to prepare for our upcoming lesson on memory allocation. Step 1. Take your flowchart and highlight all the memory operations, your mstores and mloads. Step 2. Mark the very first memory allocation you encounter in the flow. And Step 3. Collect 2 short traces that include memory writes and one that includes a storage write, or SSStore. Make sure to bring these concrete examples to the next lesson.
I want to leave you with this final provocative thought. As you trace these execution paths, ask yourself, where exactly does memory allocation fit into this architectural blueprint? How does the EVM decide to give you that space? Ponder that as you highlight your diagrams. Thank you so much for watching this Forge College Explainer. Be sure to head over to forge.college to continue your Web3 education and dive into the rest of this module. Keep exploring, keep building, and I'll catch you in the next one.